In this video, we're going to introduce the concept of electric potential. Electric potential is deeply related to the concept of electric potential energy, but it is slightly different. So our symbol for electric potential is V, and in general we will write delta V, that is the difference in the electric potential between two locations. So the electric potential is the change in potential energy of some charge as it moves between two locations, divided by the value of the charge that moved. And we'll see an example of this soon. Just following this math, we can write our change in potential energy as the negative of the work done by the electric field on a charge as it moves, which is QE vector dotted with the displacement vector. And then when we divide by Q, we get this expression here, which is negative E vector dotted with the displacement. Now, this expression here only holds true if the electric field does not vary with position. So for example, an electric field like this, where the electric field is constant at all locations, has the same magnitude and direction at all locations, that equation holds true. More generally, we can write it using this integral form here. This is valid if the strength or direction of the electric field changes as you change position. So for example, a point charge. As I move around the point charge, the strength and direction of the electric field varies. This would be an appropriate equation if we wanted to calculate the change in electric potential for a point charge. We will not deal with this equation anymore in this video. We'll deal with that in another video. Okay, now let's do an example of using the electric potential and see how it varies from the electric potential energy. All right, so imagine that we have an electric field pointing to the right. We have a positive charge here in that electric field of a value 3 microcoulombs, and it moves from its initial location over 2 meters to the right and down 2 meters. Now, using this information, we can write our charge electric field is 5 newtons per coulomb x hat. That's just a random value for the electric field that I chose. There is the displacement vector, which has an x hat and a y hat component. When I dot them together, I pick out only the x hat component because the y hat component, when I dot the y hat component with my electric field, the y component of my electric field is 0, so that goes away. And I end up with this value for my change in potential energy of that charge. Now, if I divide this quantity through by the charge in question, I arrive at negative 10 joules per coulomb, or negative 10 volts. So, a quick note on the units. The units of our electric potential are energy per charge, right? How much energy do you get per charge as it moves between two locations? That is also called a volt. This is the same unit that you see on batteries. If you have a 9-volt battery, this is what it's saying. It's telling you that you get, in this case 10, you get 10 joules of energy for every coulomb of charge that moves through that battery. If it's a 9-volt battery, it's telling you you get 9 joules of energy for every coulomb of charge that moves through that battery. One thing to notice about electric potential is that it is a property of the electric field itself, or a property directly derived from the external electric field, independent of whether a charge moves between two locations or not, right? This point here and this point here have a potential difference of 10 volts or negative 10 volts between them, irrespective of whether a charge actually moves between them. And we'll see why this is useful as we do more examples. Now let's look at another example of using the electric potential. So again, we have a uniform electric field pointing to the right. I promise this is the last time we will use this particular example. Now let's look at another example of using the electric potential. So we have a uniform electric field pointing to the right again, but this time I have drawn these vertical lines here. These vertical lines are called equipotential lines. They're called that because everywhere along this line here, the electric potential is the same. This dot product in our definition of electric potential means that if my displacement is perpendicular to, has no component in the direction of the electric field, then I will not change my electric potential. So as long as I move perpendicular to the electric field, my electric potential will not change. So everywhere along A is at some electric potential. I can assign an arbitrary value to this, just like setting the 0 point of your potential energy, we can set a 0 point of our electric potential. So we'll just call this line 0 volts. Could I call this line 0 volts instead? Yep, and then this line would be -1 volts instead of 0. Okay, so let's look at moving from our line A at 0 volts to the left and see how our electric potential changes. So if I move from A to B, plugging in my equation here, I find that the change in electric potential is 1 volt. So moving against electric field lines increases my electric potential. Electric potential increases in the same way that potential energy increases for positive charges. So if a positive charge would gain potential energy moving in some direction, your electric potential also increases in that direction. So if I imagine having like a proton here, the proton will feel a force this way. Moving against that force will gain potential energy. It will also gain electric potential. It will be moving to a higher electric potential. Okay, we can move from B to C and we will get the same value because we moved the same distance of 0.2 meters here. And if we move from A to C, we will get a 2 volt difference there. Now, another thing to note is that if we reverse a process, we will get our change in voltage back. So if we went from C to A, well, now we're moving with the electric field, which means we're going to lose electric potential. So we get -2 volts. Okay, so let's look at what happens if I take, for example, a proton and I want to move it from anywhere along my line A to anywhere along my line C. Well, it is going to experience a 2 volt potential difference. So I can use my equation that the change in potential energy looks like the charge that I want to move multiplied by the change in the voltage. So my proton has a charge of plus 1.6 times 10 to the -19th coulombs multiplied by my 2 volts gives me 3.2 times 10 to the -19th joules of energy that my proton gained as it moved from A to C. If it moved from C to A, the other way, it would experience a negative potential difference and it would give back that energy. It would have a negative this value. It would lose energy. Okay. Next, what we can look at is what if I did the same thing with an electron? I have an electron that moves from somewhere on my line A to somewhere on my line C. And in this case, we have the exact same situation, except we have a negative charge, which means that we lost potential energy. This again makes sense because if I have an electron here, it's going to be experiencing a force against the electric field, which means that it is going to be being pushed by the electric field as it moves from line A to line C. That decreases its electric potential energy. Now let's see what happens when we double the strength of our electric field. So in this setup, we have an electric field pointing to the right, but I've changed the magnitude of the electric field to 10 newtons per coulomb from 5 that it was previously. All right, well, if we look at the electric potential between A and B now, the electric potential difference is going to be 2 volts, that is 10 times 0.2, instead of 1 volt. So now in moving 0.2 meters, we have gained 2 volts of electric potential as opposed to only 1 when our electric field was half the strength. Likewise, we can find that 1 volt to the left would only take 0.1 meters, half of the distance. So I can gain the same voltage by moving half of the distance if my electric field strength is doubled. In general, the electric potential will change more quickly with stronger electric fields, right? We can see that as our change in potential is directly proportional to the electric field. A stronger electric field strength will allow us to have the same change in potential with a smaller delta X. Now let's look at what happens if we have a very non-uniform electric field. In this case, the potential difference is even more useful as long as we can measure it, say, with a voltmeter. So here I have drawn some electric field lines. All of the black lines are electric field lines, and these purple lines are equipotential lines. Notice that they are everywhere perpendicular to the electric field because the electric potential does not change when you move perpendicular to the electric field. It only changes if you move with or against the electric field. So everywhere on this dotted blue line or dotted purple line here is at the same electric potential as with the other 3 lines. I have arbitrarily named them, or I arbitrarily picked a 0 point rather of here. So because all we care about are potential differences, just pick some place to be 0 and measure your electric potential from there. So I started here. The electric field goes this way. When I move with the electric field, I lose electric potential. So all of my electric potential lines are negative in value, below 0, because I start at 0 and then I lose electric potential from there. Okay. Another thing to note about these lines is that as we move to a weaker and weaker electric field, we can tell that the electric field is weaker because the electric field lines are less dense. As we do that, the potential, the electric potential, falls off more slowly. So the distance along some field line between the 30 volt and 40 volt, negative 30 and negative 40 volt equipotential lines is longer here than this one, than this one, than this one. We have to travel along a weaker electric field for more distance to get the same change in electric potential. And so the field line or the equipotential lines get more and more spread out as the field gets weaker. Now, the nice thing about this is we don't have to know anything about the electric field if we know the equipotential lines, or if we know the potential difference between 2 points. As long as we know that, we can figure out how much potential energy a charge will gain or lose as it moves between those points. So for example, if we move from the 0 volt point to the negative 40 volt point, and say we move positive 1 coulomb of charge. So this could be in outer space and we have some free protons floating around, since protons will never move within a solid material. So we're in outer space and we have some free protons floating around. Maybe we're in the sun where there's strong electric fields. We have some protons that are going to follow these field lines, and we want to know how much energy do they gain or lose. Well, if they move from the 0 volt to the negative 40 volt, they will lose 40 joules of energy as they do that. These protons will be moving in the direction of the external force on them, the electric force on them, and therefore they will be losing potential energy when they do it. If the protons went the other way, if they started at the negative 40 volt line and moved to the 0 volt line, then they would gain 40 joules of energy because they would be moving against the electric force on them. The other nice thing about this potential is that path doesn't matter. We can choose any starting point as long as we are on this purple line. We can take any path that we want, and if we end up on this purple line here, we have lost 40 joules of energy if we're 1 coulomb of protons, right? So whatever path the protons take, if they start on this line and end on this line, they have lost exactly this much potential energy. Now that we've seen how the electric potential can be calculated using the electric field, let's see how we can actually use the electric potential to avoid having to ever think about the electric field at all. So here is the basic premise of why the electric potential is such a useful quantity to think about. First is, we can easily directly measure the potential difference between 2 points using a voltmeter. A voltmeter is just a simple measuring device that can be purchased at any hardware store. It costs about $20 and it tells you the electric potential difference between 2 points. So imagine that we have a battery. That battery could be labeled as a 9-volt battery, and if we wanted to check it, we could take a voltmeter, attach the 2 probes, so a voltmeter has 2 leads on it, and it tells you the potential difference between the locations where you attach the lead. So we could put the 2 leads of it onto a battery, and it would tell us that the electric potential difference between the 2 terminals of that battery is 9 volts. Now, if we know the electric potential difference between 2 locations, we know how much potential energy each coulomb of charge loses or gains as it moves between those 2 locations. Let's think about an example. Here is a light bulb attached to a battery. The voltmeter really just is measuring voltage here, so it's just telling us that the positive terminal of the battery has a voltage of 9 volts, the negative terminal of the battery has a voltage of 0 volts. Because we really only care about voltage differences, we can simply set one of the terminals of the battery to be what we call 0 volts. We only care about differences, so we might as well call one 0 and the other one positive 9 volts. Okay, now let's think about what actually happens in this circuit. So the things that flow in an electric circuit are actually electrons. The electrons are, in general, in something like copper wire, there are some electrons that are loosely bound to their atoms and can easily move through the copper. Protons, on the other hand, are tightly bound in the nucleus and cannot escape to move throughout the material, so protons in a material never flow. Electrons are the things that move, and we know the direction that the electrons are going to move through this circuit because we understand electric fields. So here we need to go back to thinking about electric fields just briefly. We know that the electric field points from high potential to low potential, because if I move against the electric field, I am gaining electric potential, and if I move with the electric field, I am losing electric potential. So we also know that the force on an electron will be against the electric field, which means that electrons in general move from areas of low electric potential to areas of high electric potential, or from low voltage to high voltage. So an electron is going to want to move from the 0 volt terminal through the light bulb to the 9 volt terminal. The battery doesn't allow the electrons to flow this way through it, so it can't just skip from the low voltage terminal to the high voltage terminal through the battery. It has to go through the light bulb. Now, if this is a 9 volt battery, as electrons flow through, they experience a positive 9 volt potential difference because they start at 0 and end at 9. So their potential difference, their electric potential difference, is 9 volts. And assume that we have 1 coulomb or negative 1 coulomb of electrons that pass through. We can figure out how much potential energy they lose in doing that. So we have negative 1 coulombs of charge because it's electrons. They are passing through a positive 9 volt or 9 joule per coulomb electric potential difference, meaning that they lose 9 joules of potential energy. Right? They start out at the 0 volt high potential energy for electrons state. They flow through the light bulb to the high potential and therefore low potential energy for the electrons state here. And in the process, we know exactly how many joules of energy they give up. Where does that energy go? It goes into lighting up the light bulb. So this light bulb gives off in light and heat 9 joules of energy for every 1 coulomb worth of electrons, or -1 coulomb worth of electrons that flows through it, right? As a final note, I just want to point out how terrible this problem would be to do in terms of electric field. If we say wanted to calculate how much energy the light bulb gives off by calculating the work done on the electrons using the electric field, right? Instead of measuring it with a voltmeter, if we tried to figure out all of the electric fields and then do some kind of a work calculation, right? An F.dl type of a thing. This would be really terrible because the electric field is constantly changing, right? The wires are bending, which means the direction of the electric field within the wires is changing. The electric field in different materials is going to be different. It's going to be a different electric field in the curly part of the light bulb. And we would have to figure out not just the magnitude, but the direction of that electric field at every point throughout this entire circuit. And it would be a mathematical mess to try to do this kind of work calculation using the electric field as a vector. But the electric potential saves us from all of that. We just say we know the energy or the electric potential we start at, we know the electric potential we end at, therefore we know the energy that we start at, the potential energy of our charge at the beginning, we know the potential energy of our charge at the end, and therefore we know how much potential energy it gave up. And we skip all of the electric field complexity and just get our final result.